a voltage is induced by moving a length of wire through the Earth's magnetic field. Explain two ways that the induced voltage could be increased given that the Earth's magnetic field strength is constant. We've got voltage is equal to magnetic field strength times velocity times length. We want to say what are two ways in which the voltage can be increased given that the Earth's magnetic field is a constant. Clearly we can increase the velocity if we move the wire faster, or we could increase the length. Either way, we'll be increasing the voltage between the ends of the wire as we move it through the Earth's magnetic field. It's possible a third way. If we move the wire in the same direction as the field lines, we get no voltage, and if we move the wire across the magnetic field lines, we get maximum voltage. So it could well be that by changing the direction of motion of the wire, we may be able to increase the magnetic or increase the voltage. We have a magnetic field coming out of the page here, and we bring a conducting rod downwards with a velocity v downwards. We need to draw the arrangement of the charges that result, the movement of charges that result in this conducting rod, and indicate which side is positive and which side is negative. So just imagine we've got a positive charge in the rod, positive and negative. The positive charge, we're moving the rod down. That's equivalent to a conventional current down. So in this case we have a current going this way. The magnetic field is coming out of the page, so the force on these charges is moving this direction, so we're going to get an overall positive charge on that side and an overall negative charge on this side. The question then is, if the magnetic field strength is equal to 2.8 Tesla, again a very large magnetic field strength, and the length of the rod is 0.25 meters, 0.25 meters from here to here, and the velocity of the rod, we're going to go for 30 meters per second. What's the size of the induced voltage? Remember, the little v is the velocity, large V is the voltage, and here's our equation: V equals BvL. The induced voltage is 2.8 times 30 times 0.25. The answer is 21 volt. 21 volt between here and here. If we were to put our voltmeter on here, we'd get 21 volt. Very often in the questions we're asked to say, supposing we've got an airplane traveling in one particular direction, with a velocity v, in the Earth's magnetic field. At this particular point, the magnetic field is directly down, and the airplane has got a metallic body. So what's the result of the conductor moving through a magnetic field on this? We could consider the plane has positive and negative charges. So what then happens to the positive charges across the wings of the airplane as it's moving in this direction? Let's think again. Here's a positive charge, the positive charge within the body of the airplane. The plane is traveling from the right to the left. So these positive charges moving this direction is equivalent to a conventional current going this way. the magnetic field is down into the ground, so the positive charges are going to experience a force downwards. So we're going to get an airplane which has positive charge on this side, the starboard side, and a negative charge on this side, the right side, port side positive, starboard side negative. Now the plane is travelling to the left at 290 meters per second. The wingspan is 64.4 meters, and the magnetic field strength at this time is 5.6 times 10 to the negative 5 Tesla. What is the voltage produced between the wingtips on opposite sides of the plane? And again we have V equals BvL equals 5.6 times 10 to the negative 5 times 290 times, where are we, BvL 64.4, and the answer is 1.05 volt. That's the voltage between the wings of the airplane. You could ask a question, could we then use this voltage, this induced EMF, to actually create a current? The answer is no, because to complete this circuit we would have to have a wire coming down here and across here and back. Within this wire, although it makes an apparently complete circuit, this piece of wire here would have exactly the same induced voltage effect. So the positive charges would be forced this way and the negative charges would be forced this way. So in the end we'd end up with both of these, the wing wire, as it were, the wing conductor and this wire, both would be negative, and both ends of this would be positive, and we'd get no current flowing. Another common problem is a situation like this, where we have a resistor and a wire. This way, usually a rail, that means it's a length of metal that has got no insulating coating on it, a rail at the top and a rail at the bottom, and a magnetic field at this stage sticking up between these rails, and we put across these rails another piece of metal which we move to the right, and in this case we're moving it to the right at 3 meters per second, and the wire, this conducting rod is from here to here is 0.40 meters long between here and here, and the magnetic field strength is equal to 1.25 Tesla, velocity 3.0 meters per second. So we need to calculate the size of the induced voltage between here and here, the size of the induced voltage. Let's think for again the direction. Imagine little positive charges inside this conductor. Moving to the right is equivalent to conventional current this way. The magnetic field is up, so right hand slap roll, the positive charges are experiencing a force this way. They end up here and here, and we can calculate the voltage, again BvL, capital B voltage, magnetic field, little v velocity, and length is equal to 1.25 times 3 times 0.4 equals 1.5 volt. That's the voltage which is induced across here, the induced voltage, the induced EMF. In this situation, we've now got a complete circuit, because this is a conducting rail through this 100 ohm resistor, and again back through this rail through this cable. So we've got a conventional current moving in this direction, conventional current moving in that direction, and we must find then what is the current that flows? What current flows through this circuit? What current flows? In which case we use Ohm's law. We've calculated the voltage across here, so we have a voltage equals 1.5 volt. We've got a resistance of 100 ohm, so let's use Ohm's law. R equals V upon I. In this case we want to find the current. Current is equal to V over R equals 1.5 divided by 100 is equal to 0.015 amp. That's the current that will flow in that circuit. This one now is a multi-part problem. We've got a rod across these two rails again, and we're moving this rod at 5 meters per second. What is the induced current that flows around the circuit? What is the induced current? So this is a multi-part problem. We've got a resistance. We need to find the voltage. Then we can use Ohm's law to find the current. So what's the induced voltage? The induced voltage, the induced EMF equals B VL is equal to 4 times 5 times 0.8 equals 16 volt. Secondly, we use Ohm's law, where we've got 16 volt, 20 ohm, and we need to find the current. Current is equal to V over R equals 16 divided by 20 equals 0.8 amp. And what direction is it? We move positive charges in this direction. That's equivalent to current this way, the magnetic field into the board. The positive particles then are moving in this direction. So the direction of the current, 0.8 amp. Okay, so the second part of this problem is we've got a current flowing through this circuit, a current of 0.8 amp in this direction, and we've got a length of rod, so we have current equals 0.8 amp in this direction. We've got a length of rod 0.8 meters. We've got a magnetic field strength equal to 4 Tesla. What force is on this conductor, because it's a conductor moving in a magnetic field? Force is equal to, remember, BiL is equal to 4 times 0.8 times 0.8 equals 2.6 Newton. In our direction, we have a current, we have a magnetic field, we have a force to the left. So if this current carrying conductor here is experiencing a force of 2.6 Newton to the left, what force must I be applying to the right to induce that current? Because this bar is not accelerating, the force I'm applying this direction must be exactly equal to the force going in that direction. So the force I'm applying to this bar to induce this voltage, induce this current, must be 2.6 Newton to the right. And that's a question which crops up quite often, almost exactly like that.